So anyway, I've been tasked today with talking about marine heat flow measurements. And if you have questions after the talk, you can reach me at this email address. I'm going to start talking about marine heat flow probes, a brief history of them, talk about the advanced heat flow probe that we've been developing at Oregon State University, talk about the measurements. I'll talk about outrigger probes on core barrels, and then we'll shift a little bit and talk about marine heat flow science. I'll provide a perspective by talking about past measurements, and then talk about the present and where I see the future of marine heat flow going. Okay, so just to start off, marine heat flow is really the combination of two different measurements. The thermal gradient, expressed here as dT, or the temperature change in temperature over the change in depth, and the thermal conductivity, and the product of those two measurements gives a marine heat flow determination. Over This picture shows uh, uh, a marine heat flow probe on the deck of a ship. And in general, for marine heat flow measurements, the vast majority of them are made in sediment. So sediment is required to make the measurement. In general, a probe is inserted into the sediment. Here I show a series of thermistors, and each thermistor would generate a temperature time series that looks like this figure here, where it's hanging off the bottom in this first phase. It's inserted into the sediment that generates a frictional heating signal for each temperature, which then decays, and from that, an equilibrium temperature can be derived. And so now we know the temperature at each of these thermistors. We know the spacing between them. That gives the thermal gradient. After about 7 minutes for this system, a calibrated heat pulse is fired, and the way that decays gives the thermal conductivity. If it decays quickly, the thermal conductivity is high. If it decays slowly, the thermal conductivity is low. And so now we have the two pieces of information to make a heat flow determination. Okay, so in general, that's how the system works. I think in the early 50s, the first heat flow probe was designed by Bullard. It's a Bullard probe. There was a sensor string in here, and so it was deployed off the back of a ship. And in those days, ships didn't have dynamic positioning. The ship might uh, drift off the measurement site. And then when the Bullard probe is pulled back up, it would bend. It would have to be brought back to the surface, straightened, and then redeployed. So it was a long, tedious process. Transit time, one-way transit time through the water column might be 2 to 3 hours. So it might take a day to get a single measurement. The next modification was a so-called Ewing probe. It had a bigger strength member to keep things straight, and then outrigger probes were placed on them, and they were offset from the strength member to decrease the frictional heat of penetration, decrease the time that one had to wait to derive an equilibrium temperature. But still, no in situ thermal conductivity could be made. So this was the next step in the evolution. And then finally, the so-called Lister probe, sometimes called a violin bow, because here's the strength member and then a sensitive thermistor string with many thermistors inside of it. So this gets uh, um, uh, plunged into the sediment. The thermistor string is offset from the thick strength member, decreasing the time you had to wait for that frictional heating of penetration to go away. And also with the advent of this in the late 70s, early 80s, it was also possible to put a heater wire in the thermistor string, and a heat pulse could be generated, allowing determinations of thermal in situ thermal conductivity. So you had both pieces of information. Over the past few years, so this was we had been this Lister probe is kind of based on 1980s electronics and technology. Over the past few years, we've been developing a new probe at Oregon State University. You can find more details at this website. But in general, the components include this lance, the strength member, so it's a violin bow probe, a digital thermistor string, so each thermistor is on a printed circuit board. I'll show that in a second. And there are advantages to that, including we can place many more thermistors within a small thermistor string than analog thermistors, which require two wires going up the thermistor string to the electronics. We've also included USB-L acoustics, and this serves two purposes. One, we know where the probe is in the water column. Before that, we knew the position of the ship, but not necessarily the probe. So now we know the position of the probe in the sediment when we make the measurement to great accuracy. There's a bottom water temperature sensor on board, a data logger, pressure sensor, battery packs, and an accelerometer that gives tilt. So the data logger, running everything on this microcomputer, Raspberry Pi 4 with 4 GB of memory. So one of the strategies was to be able to leave the probe in the water column, making measurements for long periods of time. Digital thermistor string, as I said, it allows more thermistors in the string. It keeps the cross-sectional area of that thermistor string relatively constant. The thermistor boards have great resolution with small amp, small power use. There's an accelerometer that yields tilt, so that we know if the probe doesn't go in straight, we know what the tilt angle is, and so we can correct for that, and that would change our measurement of DZ, the distance between each thermistor. We use sealed lead acid batteries in two independent pressure cases. It takes about 4.5 hours to charge, and we can leave the heat flow, the probe in use for the station greater than 48 hours with 1 heat pulse per hour. We also have a pressure sensor on it, so we know the depth of the probe. Uh, with one thing I didn't mention is with the advent of the Lister probe or violin probe, it's very robust. The thermistor string is sensitive, and so that we can make with a single lowering through the water column, we can make multiple measurements, and that's called pogo mode. And I'll show an example of that in a few slides. Okay, and this is just a picture of the thermistor board, the digital thermistor board. There's not much to say. They're pretty small, as indicated by the dimensions here. And there's a number, they could be adapted for a number of uses, including, each thermistor board can be soldered together, generate a long thermistor string for boreholes. Our application of thermistor strings, they could be hung in water columns. There's a whole bunch of different utilities for them. Anyway, but that's the thermistor board. Okay, as I said, we put on a Sonardyne acoustic transponder, and this makes the probe very portable. It can be used on pretty much any ship. And there's two things that this acoustic transponder does. One is it gives us the location of the probe. So on deck, we get an image like this. We know the latitude and longitude of the ship from GPS, and then through the acoustic transponder, we know the latitude, longitude, and a depth estimate of the probe. And so here, these red dots, you can see the probe. So the way the station works is deploy the probe, make a measurement, pull it off the bottom, move the ship to the next measurement site. The probe has to catch up. So you can see these red dots are the probe catching up. And then once it's within, say in this case, 75 meters of the ship, we went ahead and inserted it into the sediment. The depth here is about 2,500 meters. and we wait about 15 minutes for a complete measurement, both the thermal gradient and the thermal conductivity. And so you get this cluster of positions right here, and then pull the probe off the bottom and repeat the procedure. And that's kind of the pogo mode. And in that way, you don't have to raise and lower the probe through the water column for each measurement. We're just making a transective measurements. The other thing that it does is the acoustic transponder sends up data packets every 5 seconds or so. We get a temperature, we get a subset of readings, and in this case, this is showing a measurement. So the probe is, as I showed in that second figure, here's the bottom water temperature. Probe gets inserted here, modest frictional heating in this case, a decay to get equilibrium temperatures. Now we have the thermal gradient. Heat pulse gets fired. This is the heat pulse, and then the way that decays gives the thermal conductivity. In addition to a subset of temperatures, we also get battery voltage. So we know when we have to pull the probe off the bottom, we get tilt, we get depth, we get a number of other measurements to know that the probe is working. So if you're running a heat flow station for 48 hours, and if the probe breaks on the first measurement, you don't waste those 48 hours making bad measurements. You know that the probe is working, and you can also make kind of on-the-fly survey decisions in terms of what you're seeing on the bottom. You would know when to end a station if you're looking for a particular target, something like that. So the real-time data displays helps with efficiency. Okay, so let's see. Okay, so included with this probe is a software utilities that are written in MATLAB to analyze the data. So this shows a full heat flow station. So here's the probe, on deck right here or so. Gets lowered through the water column. Okay, and then we make our first measurement. So the probe gets inserted. We get a measurement. Probe gets pulled off the bottom. We move the ship. Probe catches up to the ship, make another measurement. In this case, this is tilt right here. This is depth, although it wasn't working for this station. And then here's temperature. So here was a high tilt and the probe fell over. So instead of waiting the 15 minutes, we could just pick it up off the bottom quickly, move the ship, and try again. And so here's a successful heat flow measurement. Repeat the process. In this case, looks like the probe tipped over or had a high tilt, picked it up off the bottom and reinserted it. But again, we got another high tilt in this case, or actually, we got a good measurement here. And then there was another one with a high tilt. So this was a hard bottom. Pulled it off the bottom, and then we got a successful measurement, although a very high tilt here. And then the rest of these look like successful heat flow measurements. So you get a data set like this when the probe gets returned to the ship. There's two parts to these MATLAB scripts, and it's recently been published in oceanographic methods. There's two MATLAB scripts. One is called SlugPen. These were written at UC Santa Cruz, where the mascot is the banana slug. So that's the reason for this prefix. But SlugPen goes ahead and looks at these penetrations and lets you parse out each penetration into separate files. Once that's done, then you can use slug heat to analyze each penetration to calculate heat flow and uncertainties. Okay, so you see the screen, you make your picks. Oops. Okay, and then you would get a screen like this. So this is an individual penetration. Okay, and again, you can see the insertion of the probe here, the frictional decay, the heat pulse, the decay from that heat pulse, giving you the thermal conductivity. Here's depth again, and then tilt. And so this had a tilt of about 6 degrees, it looks like. The program then runs and calculates a thermal gradient shown here. These are the raw thermal gradients because we know the bottom water temperature and we remove that. We set that to 0. We know the depth of the thermistors. We know the spacing of the thermistors, and we get a thermal gradient. We get a temperature for each thermistor that gives the thermal gradient. For each thermistor, we also get a thermal conductivity, and you can see that thermal conductivity increases with depth, and that gives rise to this kind of curvature that you can see in the temperature depth profile. We can account for that in the so-called Bullard plot, and this is just a rearrangement of Fourier's equation, and it takes into account variations in thermal conductivity, so we can get a so-called Bullard plot or thermal resistance as a function of temperature. And then this is just the equation for a line. So the slope of this line gives us the heat flow. And you can see how this curvature has been and this decreasing thermal gradient caused by this increase in thermal conductivity then gets removed. And so this is just based on vertical heat conduction. If there's remaining nonlinearities in the Bullard plot, then it indicates that some other process is impacting the data. Okay, so sometimes you have to make corrections to the heat flow data, and these corrections might include tilt. Might include tilt, which is automatically incorporated in slug heat. But if you were using some other software, you would have to incorporate that. Another thing to be concerned about is bottom water temperature variations. And so if there's a variation in bottom water temperature that propagates into the subsurface and may generate curvature in temperature depth profiles. So here's an example from the Gulf of California, which is relatively shallow. These are the temperature depth profiles that are offset. Here's 5 degrees. And we corrected for bottom water temperature and increased the linearity of these temperature depth profiles. Bathymetry can also distort vertical heat flow. So if you have sharp changes in bathymetry, you might have to do a bathymetric correction that's just like a topographic correction in continental settings. And then finally, sedimentation depresses heat flow. Here's a graph of how sedimentation might affect the gradient in percent as a function of the sedimentation rate and time. So in deep sea settings, this may not be needed, but near continents where where sedimentation can be more rapid, it's sometimes needed. And sedimentation always depresses the heat flow. So these are just some typical corrections that one might think about when looking at marine heat flow data. Okay, so is maybe the those using a marine heat flow probe is the majority of the global marine heat flow data set depends on those or is based on those probes, but there's other techniques. One way, and this is like a Ewing probe, is to put these autonomous thermistors on the outside of a core barrel. So during coring operations, you can get a heat flow measurement. So here we know the distance between each thermistor. We would leave the core in the bottom for about 7 minutes, collect enough data to get an equilibrium temperature. The core comes back to the surface. We haven't made a thermal conductivity measurement, but that can be made on returned core material. So this is another way to make a heat flow measurement, and this is often very important because oftentimes with this returned core material, the sediment core, you can extract the pore fluids and apply some geochemistry to get fluid flow rates, things like that. Okay, so this is just a review. Well, it's a simple review of the heat flow measurements. We've been talking about this multi-penetration probe, that is being able to operate a probe in this pogo mode. We just talked about loggers on cores. And in general, these probes have lengths between 3 and 15 meters. The longer the probe, the harder it is to handle on deck, but the deeper you get. And so if you're in areas where you suspect that bottom water temperature variations are impacting your data, you might want to use a longer probe. These are different, these are at the top are different pictures pictures of different probes. We can also put probes on ROVs, remotely operated vehicles, and make measurements. These probes are typically a meter long at most. And you cover a very small area with an ROV where you might cover larger areas with a ship. Um, so those probes for submersibles. There's also the Germans have developed this rock drilling instrument called the MEBO. Can make temperature measurements for that with IODP or other uh, drilling operations. You might log the hole while you're tripping pipe or tripping drill strings, that kind of thing. And then finally, within those, once those boreholes are drilled, they can be sealed at the top. You can put a thermistor string in them. The seals are called corks, circulation, obviation, retrofit kit. But anyway, it seals the top of the borehole to uh, to help reduce any circulation between the ocean and fluids within the borehole and get a good temperature depth profile that way. So are there any questions so far? Okay, and then finally, I just wanted to mention indirect measures of heat flow. The most common one are BSRs or bottom simulating reflectors. I'll talk about that for a little bit as gas, methane, percolates up through the sediment column. It goes into this region of stability. So down here you have sediment and gas. And then in this region right here, you would have sediment and methane hydrate, which is a methane gas. And here's ocean temperature and then sediment temperature. Here's the stability for methane hydrate. And so at this intersection is the transition from hydrate to free gas, and it's a strong, gives a strong seismic, has a strong seismic impedance because you're moving from ice to gas or sediment, and this hydrate to sediment and gas. You're slowing the seismic wave down, and you get a reverse polarity reflection. So you can see here the seafloor is kind of uh, red, blue, green, and then here you can see blue, red, blue. So it's a reverse polarity. It's a strong reflection, and it also cross-cuts any stratigraphy. So it's relatively straightforward to pick, and we can calculate heat flow. We know the temperature at the BSR based on this stability diagram. We know the temperature at the seafloor. So, and then we know the depth if we can, calculate it from the seismic reflection profile. We know the depth of the seafloor, the depth of the BSR, and so this gets the thermal gradient. And then if we have an independent estimate of the thermal conductivity, we can calculate the heat flow. So that would be an indirect measure of marine heat flow. Okay, so finally, I want to shift gears kind of from the measurements to marine heat flow, talk about kind of the past, the present, and the future. So marine heat flow observations constitute fundamental and first order constraints, elucidating a lot of physical, chemical, and biologic processes. And here's the global heat flow data set, and you can see, where there's a lot of heat flow data, where there isn't. And as part of this global heat flow day, there's this effort being led by the International Heat Flow Commission to use modern database techniques to update the global database. And so this is all part of that. And so it's an opportunity to bring all these data sets together in one repository and update the database. Okay, so in terms of past heat flow measurements in the 60s and 70s, a lot of effort was being devoted to understanding plate tectonics. And this diagram just shows global bathymetry and heat flow as a function of age. Each dot is an average over a 2 million year period. And here's the bathymetry. And the bathymetry is proportional to the heat content of the plate. So it's an integrated average of the thermal structure of the plate. And this is a plate cooling model that can be used as a reference. It's a global average, and and they comprise a reference against which heat flow observations can be made. And so here's heat flow as a function of time. And you can see that for old oceanic crust, there's a good agreement between the model and the data, but for young oceanic crust, there's this discrepancy. And that discrepancy is attributed to hydrothermal circulation. And there's really two indications of hydrothermal circulation. One is this heat flow deficit, but also a great variability. So these thin lines are the standard deviation of the data. And it's marine hydrothermal circulation is a buoyancy driven flow where at areas of exposed basement, the fluids might flow in and then grab heat or that's intercept heat that's otherwise flowing out and then uh, advecting that heat through other exposed basements. So you would get low values here, but also great variability. And it's important to note that these models represent global averages, and so any actual lithosphere somewhere may depart substantially from these predictions. Okay, so uh, these uh, marine heat flow observations are constitute these first order constraints on elucidating physical, chemical, and biologic processes. They're important for understanding overall the energy budget of the Earth. All geologic processes involve the transfer of energy, and much of that energy is in the form of heat. The Earth's geothermal heat output, of course, is 44 terawatts, and most of that heat loss is through the ocean. So, and then fluid flow through the oceanic crust is responsible for about a quarter of that heat loss. The sub-bottom thermal structure is intimately uh, connected with the creation and evolution of oceanic crust, as well as the geodynamics of rifting, subduction, seismogenesis, magmatism, and the vigorous fluid flow impacts, of course, water-rock interactions, crustal evolution, composition of seawater, things like that, the creation, generation of ore deposits. So, and a lot of the previous heat flow studies were either targeting these plate cooling models or hydrothermal circulation at spreading centers and ridge flanks. Okay, so here's another view of that. It's a conceptualization of some important hydrologic processes and properties of the seafloor. These are often viewed as a function of crustal age. So we have the ridge crust, and important thermal processes include the feedbacks between spreading rate, crustal accretion, and hydrothermal circulation. The ridge flank from 1 to about 65 million years, that's where the heat flow deficit pretty much goes away. It's globally, and circulation in this area includes globally significant fluxes of heats and fluids. The large permeability is in layer 2A, that is the pillow basalts. Driving forces are small, but flow paths can be as large as 10 kilometers or more. And then abyssal plains, uh, oceanic crustal ages greater than about 65 million years are often assumed hydrologically dead, but some local studies do show that hydrothermal circulation can extend to ages greater than that. Okay, and so here are just some examples from the Juan de Fuca ridge flank. So here we have the heat flux. This is the distance from the ridge. Here's a sediment pond. This is a seismic reflection record. Distance from the ridge again. Here's travel time and approximate depth. The red lines show the kind of isotherms derived by assuming that there's no fluid flow through the very low permeability sediment. So between the seafloor and the basement is conductive heat flow. And here are the measurements. And this just shows that the sediment pond is buried by these thinly sedimented basement ridges that is likely exchanging fluids and heat with the overlying ocean. And on average, the heat flux is 20% of what's expected, so 80% lower than what you might expect. And then here's a case where you have this basement high correlated with a heat flow high. Here's some isotherms. And it's important to note how, in general, the hydrothermal circulation is very vigorous and keeping that sediment basement interface isothermal. And also at this point, I wanted to mention something about kind of modern surveys. And so when you're designing a survey, you always want to put the heat flow measurements on top of a seismic reflection record so that you know the environment that you're making the measurement. Many ships now have dynamic positioning, and it's really good if you have a ship with dynamic positioning because when the heat flow probe is in the bottom, you want the ship pretty much over it. So when you pull it out of the sediment, it comes straight out instead of an angle that might bend it. Okay, and because hydrothermal circulation is so ubiquitous, you want to test for it. You want closely spaced measurements over relief to be able to test for hydrothermal circulation. So it's clearly present here. If it wasn't, these isotherms would be more horizontal, and so it's an easy test to see if there is hydrothermal circulation. And it's also useful, if possible, to combine with coring. You might core a spot and look for geochemical evidence of advection. Okay, so hydrothermal circulation has in the oceanic crust is generally viewed in terms of age of the plate or age of the crust. But I think it's also important to think of hydrothermal circulation in terms of the different environments. So we have the ridge environment to more and more sedimented ridge flank. And so some important questions that I think are still uh, areas of fruitful research is, how does hydrothermal circulation at the ridge crust impact the balance between magmatic accretion and tectonic extension at spreading centers? What's the nature of these thermal transitions, say between the ridge, the flank, abyssal plain? What does that depend on? How does that hydrothermal circulation impact the evolution of oceanic crust, the evolution of permeability? What are the rates and the geometry of flow? I think that we know a lot about, say, the rates of flow, but much less about the geometry of flow, certainly about the depth of flow, things like that. And then how does hydrothermal circulation wane, and does it get rejuvenated? And a lot of the early literature looking at hydrothermal circulation was in terms of sediment thickness, crustal age, but it's probably better to think about it in terms of driving forces, that is, variations in the thermal field and the near surface thermal field and impeding forces such as permeability and that kind of thing. Okay. So there's a lot of heterogeneity in the oceanic crust, and typically we trade space for time, right? So we can put all the data together as a function of crustal age, but really, each environment is different, and we need to look at it that way, I think. So we think about it, hydrothermal circulation in terms of exposed basement that ventilates the oceanic crust, focuses heat and mass, supports these biologic systems. But key unknown still is kind of how do these systems evolve as a function of environment and time? What are the scales of the hydrologic connectivity? How do transmissive and storage properties evolve with time? How do these properties relate to crustal accretion? So hydrothermal systems on fast spreading oceanic crust may be different than slow spreading oceanic crust. Okay. I think a key unknown that's up for future research is our fault-hosted hydrothermal systems. And I think with the advent of a USBL system where you know kind of the precise location of the probe, you can really target small scale features. And so transform faults that are sedimented might be one is an environment with very little heat flow data. And I think there's a lot that can be learned there, especially in terms of serpentinization, hydration of the mantle, deep ecosystems, and also these plate bending normal faults would be an ideal target to go after with heat flow data to try to understand, this if there is hydrothermal circulation impacting subduction zones and serpentinization and hydration of the mantle. Okay, subduction thrusts. Um, we know that the seismogenic zone in subduction thrusts is generally influenced by temperature bounds. It typically occurs between 100 and 150, where the 100 and 150 degrees C isotherm intersects uh, the subduction thrust and kind of turns off at where the 350 to 450 degrees C isotherm also intersects the crust. But how does hydrothermal circulation within the downgoing plate impact that? What are these? How does it impact rheologic transitions and slip styles? What's the geometry of fluid flow? How does it impact the effective coefficient of friction on the fault plane? Things like that. Okay, so those were just a few topics I think that are kind of ripe for future research. Other interesting topics that link physical oceanography and the solid Earth might be gas hydrate, methane as these shallow continental waters warm. They may destabilize hydrates, and we could look at that in terms of global change, geothermal heating of bottom waters. That is, bottom water temperature variations are often viewed as noise, but it may be signal for people looking at changes in bottom water circulation, history of bottom water changes, that kind of thing. And then finally, CO2 sequestration in oceanic basalt and peridotite is an important topic, and the hydrology of those systems is still largely unknown. Okay, I think that's all I have. I'm happy to answer any questions.